Hello! This video is to take you through the lung capacity, molar volume in human lungs lab. We're going to be talking about how to take the measurements, and I'll even do a sample calculation so that you can see what it looks like. So, there are three types of breaths that you're going to be breathing into the balloon, and you can see that on the front page. They call them tidal volume, expiratory reserve volume, and vital capacity. And if you turn to the second page, or scroll if you're on a mobile device, the second page is where you're going to write down the data. So every time you measure something, you're going to write it down on this page. So let's look at the three types of breaths. We have a tidal volume breath. A tidal volume breath is just what a normal breath looks like. You're not going to breathe in more air than you would normally inhale, and you're not going to empty your entire lungs until you're completely out of breath. You're just going to take a normal breath in and breathe a normal breath out. So this one probably takes the least amount of thinking. So I'm not going to explain too much about that. I'll just write a tidal volume is a normal breath. And you'll breathe in and then you'll breathe that breath out. That's an easy one to do. The other easy one to do is the last one, vital capacity. A vital capacity breath is as much as you can possibly breathe in and as much as you can possibly breathe out. So, largest breath. So in this case, I am going to take in as big a breath as I can possibly hold. Inhale till you can't inhale anymore, then put your lips on the balloon and exhale every single bit of it into that balloon. And you don't stop exhaling until you really are out of breath. Okay, and hold that shut so you don't lose any of it. That's a vital capacity breath. And the last one is the one that's usually the hardest to accomplish. It's called the expiratory reserve. Now with an expiratory reserve breath, the expiratory reserve breath is the one that comes after a tidal breath. So you take a normal breath in, breathe out, and notice that you have to trust me because you can't see, but I breathed out and I did not take another breath in, and I'm still talking. So in that entire time, I just took one, but in that entire time after I had exhaled a breath, there was apparently air left in my lungs. Otherwise, I wouldn't have been able to speak. This is very normal. Whenever you breathe in and breathe out normally, you are holding on to actually quite a bit of air in your lungs that's not exiting your lungs. You don't breathe out all the air. That's called your expiratory reserve. So the steps to this one. First, normal in. Second, normal out, just like a tidal breath. Third, though, and this is the only part that goes into the balloon, then you exhale the rest. So the normal in goes in, part two, the normal out, don't breathe that into the balloon, just breathe out. And whatever's left in your lungs, part three, that's what goes in the balloon. Now, where people have trouble with this, you're going to have a natural instinct to want to breathe in again. You're going to breathe in, you're going to breathe out that breath, and then you're going to try to put the balloon to your lips. We're so used to inhaling before we breathe into a balloon, if you've never done this before, which most of us have, that your instinct is going to want to be, oh, I got to take a breath, I'm breathing into a balloon. Ignore that instinct. Breath in, breath out, put the balloon to your lips without inhaling again, and exhale whatever was left into your lungs, and that's your expiratory reserve volume. And you'll be surprised at how much air is still left in your lungs when you're done breathing out, because you're going to fill up that balloon and you're going to measure it. Alright, so those are your three types of breaths. The measurement itself. You all have a green ruler, or you should. I find it easy, and you can see this is the picture from the top right. So here's the balloon. that you're holding onto with your hand, and there's the stem. So here's your, the picture is much better than me. There's like a finger here and a finger here, some fingers over here. That's your hand. Yeah. Look at the picture. They drop better. So you hold the balloon on the table, and you put the ruler next to the balloon. Okay? And you're looking for this value right here. The height of the balloon on the ruler. Assume that I drew that touching the balloon. That height of the balloon we're going to call the diameter. And it's going to be used with the graph at the bottom of the page. So if you, on that same front page, at the very bottom, you should see a graph. Okay? And the graph should say diameter here. And it should say volume over here. Now, if you want, you don't have to use this graph. The graph is there for people who have trouble with math. If you do the math, you'll actually get a more accurate answer. But if you just want to trust the graph looks something like this. You will have measured the diameter of your balloon, and let's say you had a balloon that was, so let's put some markings on here. This is like 8, 9, 10, 11. Let's say the diameter of your balloon is 9.5 centimeters. So right in here, right between 9 and 10. So you would follow that up to here, and you would look over on this side, and whatever it says over here, that's going to be the volume that is inside your balloon. Okay? So measuring the diameter up here is going to give you the diameter here and allow you to find the volume. So you'll have the volume, you'll go to the next page, and on the next page you have a big data table. Here's your big data table. Okay? With 3 columns. Now depending on which breath it is, let's just say you did a tidal breath. Okay? You would write down the balloon diameter up top. 9.5 centimeters. I'm making this up. I don't know what your diameter is going to be. Notice how they have balloon diameter 1, 2, and 3. Because sometimes you have a funky breath. Sometimes you do it weird. And so you're going to try it again. Let's say I do another tidal breath and I measure that one. And that diameter comes out to be like 8.7 centimeters. Because I apparently got excited the first time and breathed too much. I don't know. And then I do another breath and it's 8.9 centimeters. Okay? So the nice thing about doing it 3 times is I can get an average, and that way it'll help mitigate any issues you have with breathing or with measuring. All right, so those are my 3 diameters. If I take the average of them, let's see if I can do that in my head. I probably can't. Nope. So I'll just do, so you're just going to add them up and divide by 3. So for me it's 9.5 and then 8.7, 8.9. I'm doing this in my calculator, and I divide that by 3. Oh no. And I get something like 9. I get like 9.03. So my average was like 9.03 centimeters. That average is the thing that I'm going to go up here with, and I'm going to use that as my average diameter, and I'm going to use that to find the volume of my lungs. Now you should notice that that graph on the left, it has a unit attached to it. It says cubic centimeters. So if I find the volume, I'm finding a volume in centimeters cubed. Okay? Good. So I'm going to I don't have to do the math for that. I can take that volume down here and I can plug it in where it says lung volume in centimeters cubed. And there's a little picture over here, right? So lung volume in centimeters cubed. I can put in whatever my lung volume is. For 9.3, let's see if I can find it on the graph. That's about 500. At least I'm guessing that's close. You'll want to be more accurate when you look, but for me it's close to about 500 centimeters cubed. Okay? And then at the very bottom it says, what is the lung volume in milliliters? So all they're doing is they're asking, can you convert centimeters cubed to milliliters? Don't forget, this is your conversion factor. 1 centimeter cubed equals 1 milliliter. Now, that'll give me an entire, and I'll put that answer here, whatever I get. That'll help fill in the tidal volume. Now, when I go to do that again, I'm going to do that again for vital, and I'm going to do that again for expiratory, and I'll do 3 breaths of expiratory, and I'll average them, and I'll get my volume, plug it in. I'll get 3 vitals, I'll do an average, I'll get centimeters cubed, then I'll get milliliters. Sweet. Now I can go down to my questions and start answering my questions, which are the third page of the lab report. There's going to be some math here. That math is largely going to be this one. PV equals nRT. When you get down to like 5, I believe. And there are some questions at the beginning that are just generic all the way down to 4. When you get to 5, question 5, however, they're going to ask you to use your data for your tidal volume, your expiratory reserve volume, and your vital capacity. So I'm going to use my data to answer this question. So here's my data, my 500 centimeters cubed. And it says, assume that the air from your lungs behaves as an ideal gas at standard temperature and pressure. When they use standard temperature and pressure, here's what they mean. Standard temperature is 0 Celsius. Okay, it's a little less than room temperature. Standard pressure is 1 atmosphere. So if anybody asks you what STP is, you can tell them that's 0 Celsius and 1 atmosphere. Okay, so they gave me a couple numbers that I can just plug in. And then the number 5 is asking me for how many moles of gas. Okay, I can do that. Here are moles of gas. N, I want N. So I'm going to have to find everything else. P, pressure. They told me pressure is 1 atmosphere. Okay, so I got that. V, volume. I have volume. It's up here. It's 500 centimeters cubed. But there's a problem with that. Don't forget R. R was 0.0821, but it was in liters, atmospheres, Kelvin, and moles. And my 500 centimeters cubed are not liters, so I need to change those to liters before I can plug that into PV and RT. So let's do that over on the side here real quick. That's 500 centimeters cubed times, let's get rid of centimeters cubed. I know I can do milliliters, right? Remember we had it over here? I had centimeters cubed to milliliters. Okay. So let me do that. I'm going to say 500 centimeters cubed to milliliters. And I know it's 1 to 1. So for me, I'm also going to have 500 milliliters. But I really wanted liters, so I have to do one more. 500 milliliters times, let's get rid of milliliters to liters, and I know that milli of anything is 1,000. So 1 liter is 1,000 milliliters. So I'm going to get 500 times 1 divided by 1,000, which would be something like half a liter. Alright. Half a liter I can plug in, that's liters. So let's do that over here. That is 0.5 liters on the left. Okay, on the right, N is there. R, I already knew. R is always the same number, 0.0821 liter atmospheres over Kelvin moles. And then I just need my temperature. My temperature was here. It's 0 Celsius. But that's a problem because it's in Celsius, not in Kelvin. So remember our Kelvin to Celsius. Kelvin equals Celsius plus 273. Well, 0 plus 273, that's really easy. That's 273 Kelvin. And I can put that here, 273 Kelvin. Alright, on the left, I can multiply 1 times a half, and I will get 0.5 equal to n. And on the right, I have to multiply 0.0821, and I have to multiply that by 273. And I get something like 22.41. Almost done. I just have to get n by itself now, so let's do that. Let's divide by 22.41 on both sides. Gives rid of that. N will be equal to, do this on my calculator, 0.5 divided by 22.41, and I get 0.0223. 0.0223, and n should be a number of moles. And that would be my answer. That was for my tidal volume up here. I would then have to repeat this calculation again when I get my expiratory reserve numbers and when I get my vital capacity. And that should take you through most of the lab. Okay, you know how to collect the data, you know how to measure the balloon, you can use the graph. The last thing I'll say is about the graph. I mentioned before, the graph is sort of accurate if you can read it, although the numbers are fairly far-spaced. If you would like to do the calculation yourself, the calculation looks like this. The volume of a balloon will be equal to 4/3 pi times the radius cubed. Now you have the diameter, so you need to divide the diameter in half before you plug it into here. Up here, what you measured, let me show you. You measure the balloon from here to here as the diameter. The radius is half of that. So if you take half the diameter, you'll have the radius, and you can plug that in and cube it and multiply it by 4 pi over 3. That will technically give you a more accurate answer than using the graph. But that's a discussion you can have with your group members and decide for yourselves, do you want to measure your own lungs like this, or do you want to just go by the graph? Either way is fine with me. So you'll do that. Don't forget, each person has to do this individually. So you're all going to be doing the calculations, you're all going to be breathing into your own balloon if you brought it, or mine if you didn't, and measuring things, and your numbers should probably look different than the other people in the room. I don't expect people to have exactly equal lungs. Okay? If you finish this early, which is there's a decent chance that you will, you may go ahead and start work on, or finish work, I should say, on the practice problems we were doing on Tuesday. If you check Friday's website has the study guide. It has one last bit of review, some practice problems, and those practice problems have answers associated with them. There is also an answer key for the mixed gas law worksheet from Tuesday. So you're welcome to use that to check any of your answers. I'm going to be posting a video on Friday that again goes through some of these math problems and how to do them as a last bit of review before the test. Good luck.